Hello, everyone. Welcome to the Intarea at IETF 101. So we're going to get started. We have a busy agenda this time. So first of all, not well. I guess you've heard that there's a new not well. So please take a look at it. Especially, there is a privacy policy at the end that we encourage you guys to take a look. That is a new addition to the not well. All the rest pretty much the same as it used to. Some reminders: minutes are taken. The meeting is recorded. Your presence will be logged, and with Scribe, please help contribute online to the minutes. We have the Etherpad. Can we get some help from Minute Taker? Yeah? Okay, so thank you very much, Ian, for helping, but please do help Ian whenever you can to get more notes or to clarify your points if you see them. Jabber, do we have someone that can help us with the Jabber? Please. Thank you. Thanks, Mike. Perfect. So moving down to the agenda, we're going to give you guys a quick update from us, the chairs and the AD, on document status and some other topics. Then we have the presentation from Eric on the PVD, IP tunnels, a quick update from Mark if he's around. Then we have a GUI, generic UDP encapsulation from Tom. Some presentation about ILA. There's going to be the buff, but we also have a quick heads up here that's going to be presented. Then we have the presentation about the privacy and network address assignment from Tom as well. IP fragmentation from Ron, SOC 6 from Vladimir, and availability of information in criminal investigations from David. Sorry? Here it is. Okay. Could we increase the volume? Thank you very much. Yeah. All right. So moving down to this working group status update. So the privacy considerations for IP broadcast multicast protocols, it's now in the RFC editor's queue. Yes, we do. Thank you. Sorry, just a quick answer to the Jabber. We did receive the slides from the presenters, the remote presenters as well. So privacy considerations for IP broadcast, and now it's an RFC editor's queue. So hopefully soon will become an RFC. GUI, we have the presentation from that working group draft. The IP over internationally partially partitioned links, that's a draft that expired, and we encourage people to take a look. Or please, if you have interest in this topic, send comments, make a review. That would be very useful for the author. Right now, the draft is stalled because we haven't had any update on it, but we do need the community feedback if we want to advance that topic. So please take a look at that one. Probe, it's now RFC 8335, so thank you very much. Congratulations there. And IP tunnels in the internet architecture will get a presentation. So moving to the announcements, is Suresh in the room? Yeah, thanks.
Hi, Suresh Krishnan as area of the group. So we had a discussion in the IESG. So one of the documents that it came in through the independent stream, and it was trying to update or actually change things in a document that was done here, which is the recommendations for logging with ports. So what we did in the IESG is sent a note saying don't publish this because it needs to be done in Intarea because we published the original document. So that's the last document on the list over there, the draft DEVOR CGN logging. So this is personally me. I spoke to the author and he was willing to present remotely the document. And the idea is to see if the recommendations in the RFC he's talking about is whether it's practical and how we can actually go about logging the ports properly based on like what's in the servers and everything. So there's like this one contains like a inventory of what's in the servers and what's being done, what's not being done, and some techniques in there. So I would really appreciate if you pay attention to it and see like how we can update our BCP.
Thanks. Yeah, so we'll make sure that we leave enough room in the agenda for that presentation at the end. So as Suresh said, that is the one on availability of information in criminal investigations involving large-scale IP address sharing technologies. All right. So any bashing to the agenda? Hearing none, I guess we can move to Eric, please.
I'm mostly on the chair by being here. Okay, anyway, so compared to what happens last time, we got a big news, and we can show the next slide if you don't mind. Remember, kind of discussion whether we can get already an IANA code point, basically for the option we have now. So thank you to the chair and Suresh. I don't know where Suresh is up here, so thank you for this. It allows us to make the multiple implementation of sending this array option and receiving this array option to be compatible there and make more tests. We use this number 21, and I think, it's half an answer with 21, but at least we got the number. Okay, it's late, right? Half an answer, 41 anyway. Anyway, Ichaga guide is obviously not read in this room. Anyway, so we use this number for the hackathon on this weekend. Next slide. Other change. So we make the things clear. There were a lot of sections regarding using the PVD additional information. Remember, there's a JSON file that we are fetching to describe the connection based on the bandwidth of latency, for instance. We completely remove this from the text. I think it's still valuable to use the PVD JSON file to convey some transport level information, but for this draft, we remove it. If we are more interested later, let's plan for another draft and maybe another document there. Thanks to Bob, the document was a little bit fuzzy indeed, whether it was for the network layer or the application layer. For the author, it was obvious that the JSON file that we fetch after the array is for the application, but it was not in the text. So we make it clear that this additional information is for the application. We even think to change the name into additional application information to make it very crystal clear. We try to improve the security and privacy section. Of course, most probably we can maybe improve it. We made a mistake in doing the padding. All the options in arrays, so actually in any neighbor discovery message, must be aligned on 8 bytes. And we basically, at the previous one, aligning on the 4 bytes, so easy to fix. Last time in Singapore, there was a huge amount of discussion about how can we send different information to PVD-aware host and non-PVD-aware host. So the authors, we got a design meeting in a nice room in Singapore. We consider, for instance, options such as using another specific multicast group to send this array to PVD aware only. This is kind of dirty and a few other one. So we end up in an ID, not new, called container. Next slide, if you don't mind. So that's the new option. And you see that in this option, we can have at the bottom additional option like PIO, RIO, a route information option, prefix information option, every other options that can validly exist into a route advertisement can be included into the PVD option. As we need as well sometimes to include options like MTU, which are not per se an option, but are a field into the array header itself, we have the option based on the bit A to include yes or no, a repetition of the routing advertisement header. So we can have it there. Next slide. So example. Look about this one. This is the PVD ID option. It includes at the bottom 2 other options, this RDNSS and the PIO. All of them makes 4 + 5 bytes, but 4 plus 5 times 8 bytes. The ID and the header with example.org there makes as well 2 bytes by 2 times 8 octets. So the full length is 12. Okay? Actually, I counted badly, it's 3. We used it to make 12. So now, we put 12 in the length there, meaning, next slide, a PVD aware understand this option. Now he has a duty to look inside the option. And now, you know that, okay, the A flag is not set. So after the name and the padding, and we know the name is finished because they are lengths, right? The fully qualified domain name is expressed as a DNS request name. We have another option, which is RDNSS. We get the length of this one, we go to the next one, and so on. So for PVD aware, they will see not only the PVD ID, it is used to bundle all the information together and present it to the application, but they also got this RDNSS and the PIO. Next slide. And non-PVD aware do not understand the type 21 that we just received, so they say, okay, I skip it. And the length is 12, so I'm going to the option which is after. So with this, we can present PIO, RDNSS, or whatever you want to PVD aware host, while the options outside of the container are simply used only by non-PVD aware host. Of course, an array can only contain, if you want, just the PVD ID option. Okay, that's not a problem. Next slide. Implementation status, nothing has changed compared to Singapore. We make progress on Linux, obviously. Next slide. At the hackathon, as I said, we work together with 2 universities, Liège and Aberdeen. Of course, some people from Cisco, but Kyle as well from Sunvine, and another university, I forget, Wenshin from Telecom Paritech. And basically, it was the mix of PVDs on Linux, a need which is in another TAPS project, source address dependent routing, because we like this, and cap port, it was done by Kyle. Next. So that's basically all the pieces we touch, and all those pieces we're using the new IANA code. Next. So we are not ready for working group class code for sure, even if the implementation exists, and we are working for this for more than a year now. But I would love to get a serious review by this group, as well as I will ask later to 6-man and V6 ops. Okay. So review are really important. I'm more than happy to reply to questions, of course, here and during the week, but who can commit to review this document? Any chance? Any volunteer? Okay. Tom, Ted, Michael, and Jan. I don't know who's taking notes, but if you can put this in the... Oh, thank you. Don't forget to put your name, right? And for me, that's it. That's all I have to say today. And thanks again for your support for the IANA code.
Eric, I have a question.
We'll skip it. It's too long.
Can you say a few words about...
Yeah, this? Okay, if you want. Okay, I prepared some slides as a backup in case I got the question, right? So go on. Next. So we provide into the JSON file some information, right? And we use a specific well-known URL. So if you know the name of a company, you can most probably guess the fully qualified domain name and guess the URL. It's well-known, right? That's on purpose. So you could download from everywhere this JSON file. So my advice is that don't put anything confidential here, right? Because anyone can get access. And you can also restrict the access on the web server hosting this JSON file to addresses that belongs to you. Okay? Working for Cisco, I will accept only requests from prefixes allocated to Cisco, not to say another company. That's one aspect. Next. Now, even if we provide a PVD ID, that could be something like example.org or whatever, it's just information, right? We don't provide anything more anyway than array. But think about rogue PVD. I don't know whether it was really useful to do as more than an attack, but we can have, as I said, the black hat. We can have the JSON file server can be a black hat guy. the network can be hostile, and the first device can be also hostile. So they can basically send you rogue route advertisement with a fake PVD ID, or they can deliver to you a fake JSON file with wrong information. So that's how we try to do it now. Next. So first one, I am layer 2 adjacent, and I want to send you a packet pretending, hey, you are connected to corporate.com. Our regard should block it, right? That's no more dangerous than anything. So problem solved as long as you run a decent network. Next slide. So now in this case, the router is a bad guy. So you are in a hotspot somewhere, and the hotspot somewhere pretends to be, again, corporate.org, or in this case, good.com. So what you do, you try to connect to the JSON file server, and this guy is a wrong one as well, right? They fake the DNS, and they fake the certificate. Oh, but you cannot fake the certificate, right? So when you try and download the JSON file, TLS will refuse to connect. And if you have a local configuration on the endpoint telling, hey, I only accept PVD that requires the fetch of this JSON file, remember that's an option, but if you have configured to download this file and you cannot get it because the TLS session is not established, because the certificate is invalid, self-signed, or whatever, you refuse and you reject this PVD. Next. So now another one, where again, you are in a hotspot, pretends to be good.com, but this time, it does not pretend to be the JSON file server as well. So you can connect with a real SSL or TLS session and download the JSON file. Now the thing, we have in the JSON file a mandatory field key, which is prefix, which is basically in this case DB8 beef. I forgot to put a /48, sorry, in the slide. Now, when you receive it, you need to compare this covering prefix from the JSON file with the prefixes you receive as a PIO. In this case, the PIO was including bed/64. Bed/64 is not including in beef/48. You reject it. Okay, so you need to deliver not only the right JSON file, but you need to deliver the right PIO. Oh, I'm a bad guy. I am allowed to do that. Next slide. So now, I am sending, again, an hotspot. I am sending you the array, good.com. Okay, the flag is still there. Now I'm using the right, basically, v6 address, right PIO. I'm fetching the file, the JSON file, and indeed it would match, right? Because there is the router in the middle is doing NPT and nothing between the real good prefix, beef, and the bad that is used by the attacker. In this case, the protection is very simple. Again, pretty much like the confidentiality, the server will only serve the JSON file to its own address. And the request after being NATed or NPT'd is coming from bed. So it drops the request. It doesn't receive the JSON file. And again, I'm configured to use only if there is a JSON file. I don't get it, I refuse to use this PVD. Next. Now we find a place, and it's actually Pierre who is in the room, we find this, which is kind of intricate, right? We can fool everything. Nothing is really secure at 100%. What do we have now? We have a bad guy in the bottom left, which managed to get access to the real network. So is access in the beef network. Okay, and you know that the PVD is good.com. Now, with a companion somewhere, and the victim is on the top left, the next router there is sending PVD, the name is good.com, and please use the address beef as well. Remember the big arrow, or it's a tunnel, whatever you want is tunnel, right? GRE or whatever. Now, the victim somewhere on the top left receive, oh, it's good.com. Let's do it. Let's connect to the server. And then this is the small line. going via the tunnel that's routing decision proxy by the bad guy in the good.com network that goes to the server. The server sees the good source address, he serves it, end-to-end SSL works fine, right? Because the right certificate, right address. And then in this case, the attacker is able to pretend it's good.com. But honestly, it's already in good.com, so what can you do there, right? So basically, in this case, we can do nothing more, but we never pretend to be a fully secure, right? PVD are here not to secure arrays. PVDs are here to give you more information and the application layer. And I think it's the last one. Oh yeah, sorry. Privacy. So obviously, there is some minor issue is that when the host boot, he receives an PVD, he wants to get information about it, he will basically go and fetch the URL, right? Access the URL over TLS. So anybody on the path can know that this v6 address is trying to connect to this PVD, right? If the SNI is in the clear, you can even know who is there. Okay, but what's different than all our device right now here going to captive.example.com or whatever your operating system use right now to detect there is a captive portal? It's even better because normally when here, all of us in the room, except some exception, right? We do not go to our own corporation to see whether there is a captive portal, right? We go to some other vendors, which is not part, it's not the service provider, it's not the user. What indeed, when you use PVD, you stay within one operator, say hotspot or whatever. That's one thing. And we advise in the draft as well that as soon as you have used your IPv6 address to fetch this JSON file, you change of IPv6 address, and the other one is no more used. You throw it away. That's basically our status, a little bit fast explained. It's a little bit more explanation in the draft, how we can deliver some level of security, and we simply put and say that privacy, nothing is perfect, but it's way better than what we are using right now. And I think now that's the last one. Yep. Okay. Question.
Any questions? So maybe myself as individual, we have asked the security directorate to take a look to give us another point of view.
Okay, excellent.
So hopefully they will provide some feedback. I guess they were swamped by these emails, by this meeting, I mean. So not yet, but hopefully we'll get some external point of view and take a look at these answers. I don't know if everything is captured in the document.
Yeah, mostly, yeah.
Okay, perfect.
Okay,
So
thank you, and thank you for asking.
Thanks. Okay, next, is Mark in the room? No? Okay, so then I guess we can go to Tom.
Mm-hmm.
Hi, I'm Tom Herbert. I'm going to give an update on generic UDP encapsulation. So there's two drafts that I'll talk about. So one is the base GU draft that's in version 5. It is in working group last call. Not a lot of comments in the last call, but we did have quite a few pretty in-depth reviews previously. The only major change to the latest revision, GU version became GU variant. So Joe Touch had a concern that version implies kind of precedence or obsolescence of previous versions. So variant gives us a little more flexibility. So it could be kind of like a canonical version, or in the case of version 0 versus version 1 of GU, they're really different kind of variants. Version 1 happens to be a very compressed form. So just a couple of possible future updates. So one of the things we may do, the C-type field Right now, if the control bit is set in one in the GU header, this indicates a control type. It occurred to me that GU will encapsulate any IP protocol, but there are things that we may want to encapsulate in the future. For instance, another UDP-based protocol. So for instance, we could have Lisp over GU, Beer over GU. The reason to do that is GU kind of provides some general encapsulation features and capabilities. It's not really about specific use cases. So for instance, if you wanted to add fragmentation of GU to something like Lisp, we could do that. So it's a possible thing we could add. Another thing that could be pondered is formatting of private data. So GU has this concept of private data within the header, but we never really specified a format for that. Conceivably, we could add a flag field that says what the format is. So it could be some sort of TLVs or additional types of format. Could be an embedded alternative protocol. So one possibility. The other thing is GU is UDP based. However, it's not really inherent that it has to be in UDP. Conceivably, we could make it an IP protocol in itself, or Ethernet code point, probably a little easier since it has larger space. The advantage of that is would be kind of a common encapsulation protocol, similar to how GRE operates in those three modes. But in case of GU, might be a little more extendable in the future. So the other draft is GU extensions. This is in version 3, again in working group last call. Not many comments. It has received some review. The current state is there are 8 extensions defined. And like I mentioned, they're really about the encapsulation. And 11 of 16 flag bits have been allocated. So the obvious problem here is we only have 16 flag bits. So what happens when we run out of flag bits because we add extensions? The answer to that, which is actually on the next slide, the intent is that the last bit in the flag field will indicate a new set of flags as another field. This was actually an earlier version of GU. We removed it because the point was that our definition of defining flags, we wanted to define them contiguously. So in the future, once we hit the limitation, this last bit is intended to give us another set of flag fields. And then that gives us 32 more. The estimate that I think is probably pretty accurate, about 1 flag bit per year allocated, so 32 plus 5. So hopefully we have about 30 years of lifetime before we'd have to go through that again. Like I said, one of the reasons why we don't think there's going to be a lot of extensions, GU extensions really are just about encapsulation, not specific use cases. So for specific use cases, we would want to put those in a different place in the packet, either the private fields or inside, like I said, we could have an encapsulation of another type of protocol. And I forgot to mention, so we did make one major addition in the latest version of the GU extensions. That's an alternate checksum. This is something similar to UDP options. In this case, we have a CRC32, CRC16, and CRC CCITT. The reason why there's 2 CRC16s, it was really difficult to find which one kind of is more important. They're both equally used in different contexts. So UDP options, for instance, use the latter. Linux turns out it has the first one implemented. So they're both there. The good news is that it's a configuration thing. So you can only use this if both sides kind of agreed on it anyway. There was one important point, and I think this is actually coming out in UDP options also. If we make a CRC or security field or anything like that optional, and it covers the header, they do not protect the actual option. So for instance, if this were a TLV, and we had a TLV type that said this is a CRC, if that TLV type became corrupted, it would turn into something else. The receiver might not see the CRC. So the value of having the CRC goes down. I think this is one reason why we like to have like TCP checksum, UDP checksum are inherent in the packet. So that's one thing, we make a note of that. The answer here is it's a configuration option. If the receiver expects security or expects a CRC and doesn't see it, then they should drop the packet and make a note of it. The GU flag field extension, like I mentioned, it's intended to be the last bit of the flags. So the idea is I guess that the 31st bit would be the E bit, and that'll point to a new flags field. So that'd be another 32 bits. It looks like just like any other flags field, but when we're processing the flags, after the initial flags are processed, we'll hop down to that and then continue processing flags, and then fields for those flags follow that. So it's fairly straightforward. Thinking about possible new extensions, I think the OAM measurement bits, so there are two of them defined for 8321. That may be very reasonable to put into GU flag fields. Also, group-based policy may be reasonable. And as I mentioned, if we wanted to format private data, the format type may be in a field, and that would indicate what the type is of the private data. So that's all I had. Any questions?
Gary Fairhurst. I'm curious about why you think you need 3 different CRC formats. It's like, how long's your data? Is that not the only thing that would derive the choice of CRC? Interoperability seems more key to having lots of options here.
It's a 2-bit field, so we have 3 combinations. So CRC 32 kind of makes sense because that's Ethernet CRC. But the argument there is, well, that's kind of expensive. So what about a CRC 16? So like I said, it was kind of a coin toss. I did not have a strong opinion, but I couldn't find any good precedents, either within IETF or within general networking community about which is preferred. I don't think it particularly cost us anything except a couple of flag bits.
Yeah, I mean, it also costs less interoperability here. I mean, this is like creating options just for the sake of it. I mean, we chose a CRC 32, I think, in SCTP, and look at the SCTP story and you'll find why we think that's actually okay.
The CCIT one or the normal one? The normal CRC?
You can choose either CRC 32, depending on what you want and what you think is better. I mean, they don't have that much different properties. There is a document that actually discusses the difference between the two. Computationally, it's not that much more expensive than a CRC 16.
I don't have a strong opinion, honestly. If we can chuck the CRC 16, if that's fine. I would point out one thing that we did do. All the CRCs, the checksum that we have, and the security, they all have the length field. So it's kind of like a UDP light thing. So we cover, so it is optional data included. So I kind of like that aspect of it. Like I said, I don't have a strong opinion. That's good feedback.
David Black, variable length CRC hurts. You're trying to verify integrity. You shouldn't make it more complex. If you want to use more than one format, let me give you a second option and explain why it's cheaper and why it helps. The second option is to grab what's commonly known as the iSCSI CRC or CRC32C. There's 2 good reasons to do this. One is the polynomial is different. So if you're running over Ethernet, you get added check as opposed to running the same polynomial over roughly the same data. And the second is that a processor from a certain well-known processor vendor and possibly others have instructions that directly compute this sucker. So it's cheap.
So the argument was we have too many. Now you're suggesting another one.
I'm suggesting I'm suggesting a 2-stage approach. 1, toss the 16s. Now you're down to 1. If somebody would like to go explain why CRC 32 is too expensive in software, you could add CRC 32C and require everybody to do both because that one's cheaper in software.
Well, I mean, I would point out that CRC 32 is already implemented in software generally, right? Mm-hmm. So for implementation-wise, that's...
If you'd like to stop at step 1, I'm not gonna complain.
Okay, point taken. If there's a preference, then I'm more than willing to go with one. I think it's a good concept to have it in general.
So Gary Fairhurst is TSVWG co-chair. Why don't you just ask on TSVWG? Because if you want to choose a CRC, I think you'll get some feedback.
Which one?
Ask about your chosen CRC. Is it suitable on TSVWG?
Okay.
Yeah, and the transport area will give you some feedback like they did for other protocols.
Okay, that's a good point.
Thank you.
Thank you.
Thank you very much. Don't go too far away. Tom? Tom. You have two more.
Okay, hi, I'm Tom Herbert. I'll give an update on ILA now. So we have the ILA BOF on Thursday. This is a non-working group forming BOF. The intent is to highlight the problem statement, use cases. This is not intended to be an in-depth discussion of solutions. And we've had quite a bit of discussion on the mailing list. So since last IETF, there was an ILA mailing list created. A lot of the discussion gets down into security, scalability, mapping systems, denial of service threat. And most recently, there's discussion on an ILA Lisp kind of control plane. So the idea is to use Lisp control plane for ILA. So that's pretty promising. There's also been some discussions on DMM and the 5-gang and IP list. Those discussions tend to be more specific to the mobile use case. I would point out that ILA is kind of trying to be a generic, but mobile is one of the use cases. Data center virtualization, network virtualization are some of the others. And we're also looking at the 3GPP study item that they're looking at. Perhaps ILA could be part of that solution. So give a little bit of update on the data plane discussions. So ILA is explicitly not an encapsulation. And that means there are no bits added to do transformations. So we have no extensibility, no way to encode everything. In that sense, it's kind of the opposite of generic UDP encapsulation. What that means is everything needs to fit into basically the destination address. And the idea of ILA is that we transform addresses in order to get them to their destination. And before the receiver actually gets the packet, we always transform back to the original address. So it's kind of like a paired address modification. So because everything needs to fit into this small space, we have relaxed a little bit on the canonical 64-64 split. So for instance, in ILNP, there was this idea of a 64-bit locator, 64-bit identifier. That's kind of simple architecturally, but when you start thinking about different encodings and different things we might want to do, it's a little less flexible. So we're relaxing on that, and that gives us the ability to do some interesting techniques. One of the techniques is locator indexing, which we would use if we wanted to encode /64 assignments into ILA. Another one is chaining. So instead of just doing one ILA transformation, we may do multiple ones on the path. This is kind of a poor man's segment routing where we can adjust the destination address, have the packet visit certain destinations based on hop-by-hop routing. And at the very end, again, the packet has to be transformed back into the original packet so that the receiver has no idea that this happened. This does represent a bit of a trade-off. So in order to keep the data plane simple, that implies a little more complexity in the control plane. So that's kind of the ILA trade-off. The control plane pretty quickly gets to identifier locator split, scalability type of issues. And this has a lot to do with mapping systems. So in identifier locator split, we do think there's going to be mapping systems. So imagine a large network, everything is somehow virtualized or mobile. We need a way to find out where identifiers are. Identifiers are basically the logical nodes. So for that, we need a mapping system. This is pretty accepted in the identifier locator space. So the question right now is how to do this mapping system. It's a little independent of ILA. I think there are some things that ILA kind of implies in the mapping system. But fundamentally, the mapping system does have kind of 4 pillars, the scalability, security, privacy, and DOSability aspects. So I think a lot of that will come out in the ILA BOF, maybe in a little bit more detail. But again, the solution, it's about the problem statement right now, and the use cases a little bit less on the solution. So again, that's Thursday, 1810 in Viscount.
Thank you very much. So that's a teaser for the BOF that will take place. And in the interest of time, maybe we can move to the next presentation and leave discussion for that BOF, if that's okay. Next, Tom.
Okay, one more. So this is kind of an offshoot of some of the things we've been looking at ILA. And this is particular looking at the privacy and prefix assignment. So I will give a few caveats up front, just to make it clear. So this is only considering privacy at the networking layer, specifically in addressing. Privacy itself on the internet has to be considered every layer. We know that this is considering one aspect of that. This is also only considering risk from third parties interpreting or inferring information from IP addresses. So that specifically means we're not considering network providers that have, say, the full mapping of IP address to device. It's up to them to secure that data. I'm not sure we can do much technically to solve that problem. And equivalently, this doesn't address law enforcement or authorities who can compel, say, network providers to release that information. So, like I said, those are caveats up front. We understand that, and privacy is a multi-pronged problem, as we know. So, what about prefix assignment? So, /64 addressing to host is actually becoming quite common. So, Slack, for instance, is doing that, and it's actually pretty common in mobile networks. UEs get full /64. This is actually recommended in RFC 3314. So that gives us some properties. And since the prefix is being assigned to the device, that means there's kind of a one-to-one relationship between a prefix and a device. So given two addresses that share the same prefix, even if the IID is different, the interface identifier, in this scenario, they actually would refer to the same device. And that becomes a little more problematic in the case that we're assigning to, say, a UE in a mobile network like a smartphone. Then there becomes a much higher probability that that device actually corresponds to a specific user. So now we have a one-to-one relationship potentially between the prefix and an actual user. And another issue, prefix may contain fine-grained hierarchy for routing. And that's going to have to do become a problem if that reveals location of the device and hence the user. So the privacy issue is kind of implied from that. The prefix becomes an identifier for the device. The addresses are used in the public internet. So if a third party knows that a site is assigning prefixes, then if it sees two addresses, it can infer that they are the same device if they have the same prefix. So this exposes the risks of revealing user identity and communications and location of users if location information is actually encoded in the prefix. So this specific issue was actually raised in RFC 4941, 7721, maybe some others, and periodically changing the interface identifier in 4941 actually is no help because the potential problem is in the prefix, not in the interface identifier. So we could extrapolate from RFC 4941 to just change the prefix periodically. And conceptually, that's possible. We do know that changing addresses, if there's only one, if you change it periodically, it would probably kill all the existing flows and they'd have to be restarted. So assuming we solve that problem, then the real question becomes, what is the correct frequency to change addresses in order to ensure privacy? And it's a tricky question. I did pose this on a couple of lists, and there really isn't a very good answer because someone could say a day or a week or an hour, and there's no way to quantify what kind of privacy you get out of that. So the conclusion that I postulated was anything less than a different address per connection or per flow theoretically could have a privacy exploit. And I actually gave an example in the draft, you can read it about a proposed exploit that could take advantage of that. So any reuse of a prefix or address could be exploited to figure out identity. So from that, we can consider what are we really shooting for in the privacy and addresses. So I give an example of a couple of criteria, and this is based on if I have two addresses and no other information, what can I infer from these two addresses? And it is obvious that you can infer they're from the same provider, same organization. So they will share a common network prefix. That's kind of basic. And it may be also that they belong to a very broad geographic grouping. So it would be expected that a large organization would probably want to have some geographic or regional hierarchy. But beyond that, the idea is the viewer of these addresses should not be able to deduce any other information. Specifically, they can't tell that the nodes that are associated with these addresses are not the same node or in the same rack or at the same location or have any other proximity. So that's, I think, kind of I don't think it's strict. I think that's just some criteria for privacy addressing that we'll propose. Now, I would point out that network address translation, NAT, can actually meet these criteria if there's a large enough address pool. Because basically what NAT does is it obfuscates the underlying addresses of the network, and what you get on the wire, on the internet, is the address of the NAT device and some port number, and the port number refers to the specific instance, but external users, they don't see that. So it turns out NAT actually meets these strong criteria. As pointed out in the document, I do think this is one reason why some law enforcement agencies are a little paranoid of NAT, because it does in a sense, such a good job of hiding identity. So the document does present a possible solution, and like I said, this kind of was a sub-problem of NAT, or not of NAT, but of ILA. So with identifier locator split, the idea is that we can use identifier locator split so the identifier becomes independent of location, and we can assign multiple identifiers, hence untrackable addresses to host. The addresses still share a common prefix, but if this is done with enough randomization, they would share nothing else. So two addresses assigned to a host, the same host, would have nothing in common except that prefix. So that would meet the strong criterion of privacy and addressing. So for maximum privacy, then because of the result that we need to use an address per flow means we have a lot of addresses potentially. That's obviously a scaling problem. So looking at some of the potential mitigations there, one thing is not everyone necessarily needs this privacy. So in some sense, this could be a service. If somebody really needed that level of privacy and wanted the one-time use address, this could be a way to accomplish that. Maybe there are other communications aren't necessarily that private and they don't need that. Obviously, that's not a great solution because now we're forcing the user to make a decision, and we'd rather give them perfect privacy all the time. So another way to look at this problem is what we're actually trying to do. We actually want to aggregate addresses as belonging to the same host, so we can get the addresses to the right host, and that's the problem that the mapping system has. So there is aggregation here. So the question we're pondering is, can we do a sort of hidden aggregation where the network can assign a host a block of addresses, and to the outside world, this block looks completely randomized. However, the network, either through some sort of public key encryption or some type of hash, is able to deduce that these addresses actually aggregate to the same node in this case. So this is the concept of hidden aggregation. So the first level would be local network has a way to create these addresses, assign them to the host, and only the local network would understand this. If that problem is solved, then the question becomes, how do I do a bulk aggregation? Because we still don't want to have to give host individual address. Theoretically, they could require thousands or millions of these. Is there a way to give a host a way to create a block of addresses itself? And whenever it needs a new address, it can create an address. Say we give it blocks of 64,000 IP addresses, and it can use them as needed. And when it runs out, it can ask for new ones. So those are kind of some of the things we're looking at. And again, this is kind of along the lines of how identifier locator may solve that issue. Any questions?
Hi, Tim Chan. I've got more points than I should probably make here, so I'll just say a couple, take the rest of this. So I think the first one is, I think this is useful, having per prefix privacy. I think if you compare it to the privacy for hosts as it stands, you're probably going to want to be able to have persistent prefixes and private prefixes. So you need to be able to somehow delegate a prefix that's marked for use as a kind of a privacy prefix, I guess.
We would do a block, some sort of block delegation where it's not a prefix, right? It's actually a block for privacy. Is that what you're referring to?
Well, if I was, say, for example, something was being allocated to my home network, for example, then maybe having a rotating prefix out of the ISP's prefix that I can use to initiate new connections from would be a good thing, while I've still got a persistent prefix that I can have my services on without running dynamic DNS or other things to update and essentially have to renumber my network every time you give me a new privacy prefix. I think would be important to know.
Well, I mean, so I'm not sure it's so much renumbering, right? It's more temporary address assignment, I think is the best way to phrase it. So the addresses could be requested on demand in some sense. So obviously, if you want a persistent prefix because you're a server, then that might be a different story.
Yeah, but otherwise it seems you're potentially going to assign me addresses that might be shared between multiple customers or something, and that starts getting quite, well, it shares lots of problems that we have with CGN and so on today, doesn't it? I think as a user, I think a lot of users are aware of privacy issues, and that's why they use VPNs like Hide My Ass or whatever other ones they fancy using, or Tor or whatever. So I think there's some awareness there. I think what we're trying to do here is perhaps provide some more subtle privacy that the users may not ask for, but I would like them on my own network to not affect the things that I'm running as services in my network. I think the problem with doing this big block and giving a host a zillion addresses that it can use, you run into all sorts of the other things that have been discussed before, things like ND cache exhaustion and so on. There's all sorts of things that if you try and use an address per application are going to hit you in other ways.
I imagine there's a lot of legacy towards this, right?
I think it's a very good topic, but I think just throwing ILA at it is perhaps an answer, but I think there's more pragmatic things that need to be considered first.
Okay, I'm cutting the line now here. We had someone in mid-cycle. I don't know if Dave still wants to have his place, but Lorenzo?
I think stating the goals like you stated them is sort of misleading. At the beginning, you said it is entirely out of scope to think about anything that the ISP can do to attack privacy, or anything that anyone that has the power to compel the ISP can do. You declared that to be out of scope on slide 1. But it doesn't mean that just by making it out of scope, you can, there is a privacy trade-off there. For example, a scheme like the one where you assign, let's say that the ISP assigns you one IPv6 address for every different connection, right? Yes, you can declare ISP sort of privacy to be out of scope. But the fact of the matter is, if we build this scheme, then the ISP has to maintain a record of everything that you did. Whereas in the case where it has to keep essentially every TCP connection, right? Whereas in the scheme where the ISP just assigns you a prefix that rotates, they don't have to keep all that information about you. So yes, you can declare it out of scope, but you're basically moving a slider around where different parties have different views of how much activity, of what activity you conduct online, and the solutions here are basically all on the other side of that slider because one side of it's out of scope. But I think that's not a full solution to the problem.
Well, so let me ask a question. So NAT exists today, right? And NAT is not prefix assignment in the sense. So externally, what you get with NAT is something that apparently is randomized. So as far as I know, most ISPs are required to keep all NAT mappings, correct?
No, I don't know that. I don't.
Well, but the data is the same. So NAT effectively gives you a different source address per connection as far as the outside world's concerned. So if they want to do attribution,
NAT
you have to know the
doesn't
NAT
do-
mappings at that time. I think that's the argument that law enforcement's making, but it's not clear to me why that argument is, because it seems like the NAT logs are sufficient, in which case if the NAT logs are sufficient, then the logs of address assignment in this case should also be sufficient. At least that's my understanding of the problem.
So it's not clear even, I mean, it sort of becomes pretty murky because it's not even clear whether the party on the other end, like the server, actually keeps source ports, right? So,
Well, right, but the server is a different thing because the server can be anywhere on the internet.
if you don't have the source port, there's nothing that can be tracked, right?
Well, no, if I know what I'm looking at, if I know the NAT translation, then I can reverse engineer who was sending that.
If you're behind in that, if you have the logs, yeah. If the NAT keeps logs. But like I said, I think it was not necessarily a specific suggestion about these points. I think basically declaring that attack vector to be out of scope is an error because it means that because it means that any solution that entirely gives the ISP and anyone with access to the ISP all this information, basically we're completely disregarding that downside because of the way we set the goals.
Right, but they already have all that information.
No,
right?
that's not true.
Well, they do have that because they have the prefix to device information. They have to have that.
But they don't have to track every connection.
But you don't have to track every connection here either. What we said is you can assign addresses to devices. They can use them however they want. It's not necessarily per connection, right?
That's right, not necessarily, but like I said, the one scheme that you proposed was different address per connection. That requires 100% participation from the person that's routing the packets to that address.
Yes, but
my point is on that last slide where you proposed several different arguments, the only difference between those is the amount of information the ISP gets, which on slide 1 you declare to be out of scope. So I think that's kind of disingenuous.
Right, but look at it this way. If I assign an address now and they use it only for one connection, then they only use it for one connection. The ISP doesn't know what connection they use that for. It's not like NAT. Now you actually have more information because NAT is about the actual connection. This is, I mean, I know it's a subtle point, but this is just the address assignment. That's what needs to be tracked. The request doesn't say, I want to create a connection to this destination, give me an address.
But you
the request
know
just says, give me an address.
But you wouldn't know, like I'm saying, I'm talking about the goals, not the proposals.
Okay, so you say the goal, we have to do connection tracking, is that?
The goal is that we have to provide privacy and we can't just wave our hands and say whatever the ISP sees is out of scope. Because one scheme that satisfies your goals entirely is that the ISP logs every 5 tuple.
No, but
it is.
What I'm saying is
satisfies
that's
your
not
scheme.
part of this. Well, NAT satisfies that too, right? So we're trying not to do NAT.
Okay, we can take this one to the list. Maybe we go to the next one on the line. Then we have Mitico and the last person.
Hi, Kyle Rose. This might be a dumb comment, but if we're giving 2 to the 16 IP addresses to every host, could that actually lead to ISPs with millions of hosts running out of IPs? I mean, I know IPv4 is big, but 2 to the 16 is pretty big too.
As opposed to 2 to the 64th that they're getting today.
Oh, so are we talking about handing out like /96s or something?
Blocks of 2 to the 16th, 128-bit addresses. Sorry.
Okay.
Not prefixes.
Sorry, that wasn't. That makes more sense.
Okay, thanks. So next we go to Mitico. Dave.
Hi there, it's Dave O'Reilly here. I'll be speaking later, but I just wanted to jump in with a couple of points about, I guess you could call it the law enforcement perspective on this. I'm not a law enforcement officer, but I do work with them a lot and I understand their perspective. And the perspective on a situation like this would be that if there has been some criminal activity and that activity is associated with a particular IP address, what the law enforcement officer is going to be interested in is who was controlling that IP address at a particular time. At the moment, almost everywhere in the world, I can't speak for the entire planet, but everywhere that I've ever worked, it has been a requirement, a regulatory requirement on ISPs to be able to identify their customers. And this touches on what I'll be talking about later, but it seems to me that whether a whole block of 64 IP addresses is allocated to a particular person, to a particular host, or whether the IP address has to keep connection logs, there are two solutions to the ultimate problem, which is that ISPs will be required under regulation to be able to identify their subscribers. Now, so that was my first point. Whatever way it pans out, that's going to be the case. The other point that I wanted to make was, I am of the opinion, I hope this is not too controversial a comment, that for a plethora of reasons, connection logging is a terrible idea. And the main reason I think is the risk of loss of that data is huge to the privacy of the individuals concerned. So ISPs have data breaches just like everybody else. And if all my connection logs got out, they can see everything that I was browsing at every moment and so on and so forth. Which is why I'm resistant to that idea. So as long as there is some alternative mechanism by which individuals, like ISPs, can meet their regulatory obligations to be able to identify their subscribers, that's really the point that I wanted to make.
Okay, those are good points. But again, I point out that this solution actually is not connection logging. It's more address registration. So it's effectively what we have today with a prefix to device, but it might be greater scale, so it'd be address to device. But it wouldn't be going as far as NAT, which is clearly connection logging. So that wouldn't occur. And I'm assuming that law enforcement has to have NAT logs today already. So it's kind of like that component, at least in terms of scalability, should already exist as far as I can tell.
So NAT doesn't require connection logging. You can do that, but you don't have to. Port block allocation.
So you're
like
logging
I've heard
the
this said so
source
many times,
port,
you don't have
source
to get
address.
it.
Okay.
You don't have to log all the connections just because you're running that.
Okay, great. So that's less data.
Like, you can, but it's really like the logging requirements are just enormous.
Thanks. So last person on the mic, please.
Hi, Nick Doty, UC Berkeley. I'm coming a little bit new to this area. I work mostly at the web level, but I'm particularly curious about, you were talking about the timing of rotating identifiers. And I feel like there's a particular concern about like that if we have too many identifiers that are getting rotated at different times, we might lose the privacy benefit of rotating identifiers. So I'm curious about like whether the client has control or whether the client's like, or having some guidance so that we're rotating all the identifiers at the same time. Otherwise, all the end servers can just line them up and actually sort of figure out every changed identifier.
Okay, so real quick. So one, I think the client should have the control. Client gets addresses from the provider. Client should use them as it sees fit. So I think that's pretty clear. Two, please look at the draft because I give the example potential exploit that could defeat any frequency except once per connect or one per flow. That example hasn't been refuted, so it may be accurate. So if you have any ideas on whether it could actually happen, I foresee this. One thing I think is privacy is probably such a big problem that maybe the attackers haven't gone down to this level yet, but I do think it's going to be a problem at some point.
Okay, I'll follow up. Thanks.
Thank you very much. Yep, fine. Thanks a lot. Ron?
Keep it short. Okay, I can do that. Hello, Ron Bonica. The chairs have asked me to shorten the presentation up a little bit, so I'm going to skip over a couple slides. This draft used to be called IPv6 fragmentation considered fragile. And as we were writing it, we realized most of our criticisms applied to IPv4 as much as IPv6. So we renamed it. It's now IP fragmentation considered fragile. What are we doing in this draft? Well, we've known for a long time fragmentation reduces the reliability of internet communication. In this document, we're going to talk about what fragmentation is a little bit. In fact, we do it in the document. We'll skip over it in the presentation. We'll talk about how fragmentation reduces reliability. And we'll put out some recommendations for protocol developers and network operators. Now, keep in mind, we're not talking about deprecating fragmentation. That just can't be done. What we're talking about is pointing out how it makes it, how fragmentation makes communications fragile, and strongly recommending that protocol developers wean themselves off a dependency on fragmentation. So there's some terminology you need to know to play the game. I'll assume that everybody in this room knows what an MTU, the minimum link MTU, and PMTU is. I'll also assume everybody in the room knows how IP fragmentation works. I'm just going to point out two things. One is a small difference between how IPv4 fragmentation works and IPv6 fragmentation works. In IPv4, you have this thing called the DF bit. If it is set, a packet cannot be further fragmented downstream. If it is clear, a packet can be set further fragmented downstream. In IPv6, there is no DF bit. A packet can never be further fragmented downstream. It can only be fragmented at its source. The next thing that fragmentation has in common between IPv4 and IPv6 is when you fragment a packet, you divide it into pieces. The upper layer header always appears in the first fragment. It never appears in subsequent fragments. This observation about where the upper layer header is what brings half of the fragility into the argument. Now, in an environment where only the source can fragment a packet, the source of a packet needs to do one of three things. Either restrict itself to sending packets that it knows will never be fragmented. That's for IPv6, never sending a packet bigger than 1280. For IPv4, never sending a packet bigger than some arbitrarily small size. So that's one thing it can do. Another thing it can do is PMTUD, path MTU discovery, so it discovers the MTU of the path ahead of it. And the third thing is packetization layer PMTU discovery. And we'll talk about each of those for a second. PMTUD, the source node makes an initial estimate of the PMTU to a destination. That estimate may be too large. It then starts sending packets to the destination. If the packet is larger than the actual PMTUD, the actual PMTU, it will not be forwardable. It'll get dropped, and a downstream router will send an ICMP packet too big message to the source. The source, having received that, will update its estimate of the PMTU. Now, this strategy, PMTUD, absolutely requires the network to be able to deliver ICMP PTP messages. If it can't do that, it's black hole time. The next alternative is PL-PMTUD. Here we push the problem up to the packetization layer. The packetization layer, let's say TCP, in band sends packets of different sizes to its TCP peer. What it's doing is probing to find the PMTU. It relies on two things. Primarily, it relies on acknowledgements of its probes at the TCP layer. It can also rely on ICMP feedback, but then again, it's perfect in PL-PMTUD. The endpoint is perfectly able to ignore the ICMP messages. It doesn't need them at all. PL-PMTUD is defined for TCP in RFC 4821. It's being defined for some other protocols in draft Fairhurst going on in the TSV working group. Sadly, it's not defined for UDP, and it can't be because PLPMTUD kind of assumes a long-lived session, well, a session, not a one-and-done packet. The other thing about PLPMTUD, it doesn't rely on ICMP PTB messages at all. If they're all dropped, PLPMTUD still works just fine. So, we've talked about the status quo. Now it's time to leap in and talk about why is it that fragmentation makes communications unstable or fragile? Well, one problem, these problems all link back to the problem that only the first fragment has the transport layer header in it. What are the impacts of that? Well, let's say for a minute you're a load balancer, and you're a load balancer that load balances on TCP ports. If the TCP port is only in the first fragment, you're bound to suboptimal load balancing. Next issue is firewalls. Let's say you're a firewall and you have a rule that says block all packets based on the TCP destination port. Well, you can configure that firewall two ways. One way is to accept all subsequent fragments. That's a little bit too liberal. Another way is to drop all subsequent fragments. That one's a little too restrictive. There's no healthy middle ground. Other middle boxes can have the same kinds of problem because they need access to the TCP header or the transport layer header. For instance, let's say you're a middle box that's remarking the DSCP based on the TCP port number. It's fine for the first fragment. What do you do for fragments 2 through N? There are some other well-known problems with fragmentation that don't have to do with the transport layer header not being in subsequent fragments. There are bunches of security vulnerabilities that have been documented over the years. Overlapping fragment attacks, like the Rose attack, resource exhaustion attacks, and many more. We won't go into them now. They're in the draft. But there's an interesting problem around TCP loss, around ICMP loss. PMTUD fails when you're losing ICMP packets. ICMP packets can be lost for bunches of reasons. One is because network operators are filtering them. They shouldn't. There's an RFC that says they shouldn't. Another is just plain old packet loss or rate limiting. Those things happen, but they're not insurmountable problems. There is at least one insurmountable problem, and it has to do with Anycast. I'll give you this example from Jeff Houston's work. Let's say for a minute that a DNS client sends a DNS request to an Anycast address. It's a common thing to have happen. It arrives at a DNS server. The DNS server sends back a very large response. It's running DNSSEC, so the response is going to be big. People are laughing. That response gets to a point where it cannot be forwarded because of an MTU problem. So the node that could not forward the DNS response sends an ICMP message back to the source of the packet. The source of the packet is an Anycast address. And it goes to some DNS server that has that Anycast address. Unfortunately, not the one that sent the packet that's problematic. It's black hole time. Another problem is network operators tend to filter fragmented packets. There are two studies, one by Fernando Gant and another by Jeff Houston, that demonstrate this. We don't quite know why they do it. We just know that they do. So, time?
Yep. Well,
okay. We have some solutions at the transport layer. We've talked about them already. We'll go quickly. Let's get to the recommendations so I can yield the floor. We have some recommendations to application developers that they should not develop applications that rely on IP fragmentation. And what's more, if there are any that are crucial to the internet infrastructure, they should be rethinking those applications so they will rely less on IP fragmentation. The next is for network operators. They must not filter ICMP PTBs. That's already in another RFC, so it's not crucial. But the big one is for DNS, and especially when DNS is using DNSSEC. They should be finding ways to not rely on IP fragmentation. And anyhow, the ask, next steps is to adopt this as a working group document.
Okay, so can I have a raise of hands? How many people have read this draft? Okay, quite a good, actually, to be starting. So as you know, we're running out of time, so maybe I'll take one question, and then we keep moving. We'll take it to the list, I think, before adopting as a working group, but that's a good show of interest in it.
David Black, I'm here for Transport Area, and I'm here to help you. Ron, I'm going to say a dirty word, tunnels. Please make sure that what you do here is lined up with the Intarea tunnels draft, where fragmentation is used to solve some nasty problems with tunnels. We really ought to have a consistent story across the two of them. Thank you.
Okay.
Thanks a lot. So Vlad?
Hi, so I'm going to give you a quick update on our work on SOX version 6. I'll start by giving you a brief overview of where we're at. So we've trimmed down the RTT, the overhead in terms of RTT down to 0 if zero RTT authentication is used. In order to protect it against malicious third parties, we've taken a step back, and rather than having SOX provide encryption, we've decided to run it over TLS and then handle whatever issues TLS has. Notably, TLS early data is prone to replay attacks, and we have a mechanism that mitigates such attacks. Now that we're also running SOX over TLS, plain text password authentication is actually viable. And finally, we've added a new we've leveraged SOX options to add a new setSOC-opt and getSOC-opt-like mechanism, and we've used it to implement some stuff related to MPTCP. More on that later. So SOX version 5 starts by negotiating the method of authentication. Then it does the authentication. Then the client requests that the proxy establish some connection to the server. And then finally, application data can pass through. SOX version 6, in contrast, sends as much data up front as possible. So we cram in the authentication method negotiation and the address of the server, and also some application data. We cram it all into the first message sent over to the proxy. And of course, if zero RTT authentication is used, the server sends can send an operation reply as soon as it establishes a connection through the remote server. Speaking of zero RTT authentication, this is how password authentication is done in a zero RTT manner. So RFC 1929 describes how password authentication is performed for SOX. Basically, we can just take the initial message sent by the client, which contains the username and password, and place it inside a SOX authentication data option. Now, of course, there's a small caveat to that. If the username or password are exceptionally long, it simply won't fit in that option, and you have to do it the old-fashioned way, which takes up one extra RTT. However, this is unlikely. Next up, we've got socket options. There's been some discussion on the mailing lists. Notably, David, he brought up the point that sockets are actually an OS construct, and connections aren't necessarily, TCP connections aren't necessarily done using sockets. So we're going to rename these options in the next version of the draft. Now, clients can use these options, can include these options in their SOX requests in order to request certain behavior from the proxy, and proxies can include them in operation reply to advertise their behaviors. The fields I want to draw your attention to are level, code, and data. So the leg basically indicates what leg the behavior refers to. It can either be a client proxy leg, the proxy server leg, or both legs. Then the next three fields were actually inspired by setsock_opt and getsock_opt. We've got level, operation code, and data. For possible levels are a generic socket level. Then we've got levels for the layer 3 protocols, namely IPv4 and IPv6, and 2 more levels for TCP and UDP. We've used these socket options to handle TFO. So there previously was a field in the request which indicated whether or not the proxy should attempt to use TFO. Now we've removed that field, and when a client wants the proxy to use TFO, it simply includes this option as part of its request. The absence of such an option means that the server must not attempt to use TFO. Next up, we've also used these options to implement a use case called proxy bypass. So let's say that a mobile phone has both a Wi-Fi and a 4G interface, and it wants to take advantage of both interfaces. Now, as you probably know, MPTCP deployment is lagging behind on the server side. So if let's say a mobile phone wants to take advantage of both of its interfaces, it probably has to go through a proxy. Now, some servers might start deploying MPTCP. Now, in case a server does support MPTCP, the proxy can place an MPTCP option in its operation reply, signaling to the client that the upstream server does indeed support MPTCP. Then the client can forego the use of the proxy and talk to the server directly in further connection attempts. And finally, we can use these options to change the MPTCP scheduler used by the proxy. So clients can place such a request to indicate what packet scheduler they want. We currently support the packet schedulers available in the Linux MPTCP implementation. And proxies can include them as part of operation replies to tell clients what schedulers they are using. We found one possible use case for this option, namely low latency services. So if a client wishes to have low latency, it can tell the server, it can tell the proxy to duplicate data across all MPTCP subflows such that the delay is always minimal. And with that, I'll be happy to take questions.
Thanks. Can I have a raise of hands? Who has read the latest version of this draft? Okay. And who has read any version of this draft? Okay. So we definitely encourage people to comment on this latest version. If you can, please take a look and send comments to Vlad. Thank you very much. We are running short of time, so we're going to be moving on now. Thanks. So next is Dave, remote. Dave?
Hello?
Yeah.
Yes. Hi. Okay, so hello, everybody, and thanks for the opportunity to present this. I'll be as close to 5 minutes as I possibly can. So now, next slide, please.
Yep.
So I'd like to begin by describing what the currently published best practice is, which is RFC 6302 on logging recommendations for internet-facing servers. Okay, so what that document recommends is that as well as logging incoming IP addresses, servers also log incoming source port numbers and timestamps and transport protocol as well. But why? And the answer is because of large-scale address sharing technologies such as carrier-grade NAT. In the presence of these technologies, this additional information is required in order to attribute the activity of an IP address to at the very least to an ISP, but ideally then to an individual from a crime investigation point of view. So in the presence of large-scale NATs, IP address is not enough. You need this extra information as well. That's not to say that if you did have all this information, you would successfully be able to identify an individual from this. It's just the information that is required to address the problem that is presented by carrier-grade NAT and related technologies like IPv4 to IPv6 mapping technologies. Very similar problem. Next slide, please.
Okay.
So I did a little bit of research, and what I found was that whilst those recommendations, that's fine, they are what they are, but they're not enough. And here are some of the issues that I identified. So somebody who was considering implementing those recommendations might find that their server software might not support logging of source port, and that would prevent them from being able to achieve the recommendations. Another thing that I have seen is that certain server software, the only way that you can enable logging of source port is by enabling a ridiculously verbose level of logging, like debug logging or something like that, which you're never going to do on a production server. So whilst it may be technically possible, it's infeasible to implement source port logging. Now, practically no server software enables it by default. And indeed, no server software that I could find, bar one, even has a default configuration sample that includes logging of source port. So somebody trying to do this is battling uphill. There's not even a default for them to enable. Now, the next point that I wanted to raise with the existing recommendations is the existing recommendations recommend that you log against some sort of traceable time source or some sort of central time source like an NTP server or something like that. But there's a whole plethora of deployment scenarios where that's not possible. And nor is it actually necessary for the requirement of the BCP, of the best practice, which is to be able to identify enough information to be able to ask an ISP who was using this IP address at that time. Because I'll take a moment to explain why you don't need to exact timestamp. It's pretty well known in the forensics world. It's one of the first things you learn as a forensic examiner, that you don't need to know the exact time which something happened at. All you need to know is the time that was recorded. And as long as the time is recorded consistently, you can offset the time then to be the real time. So if you are analyzing a computer, for example, and its time is set 1 year wrong, you can look at all the times on those computer, compare them to real times, and then offset all the time. So you know, as long as time is recorded consistently, it doesn't need to be recorded against a reference time. So I take exception with that point in the recommendations, in the current recommendations. And then the last point that I wanted to raise for whatever it's worth, which is logging information doesn't exist in a vacuum. People log information for a reason. And oftentimes people have all sorts of scripts and tooling and so on that's built based on their logs. And by changing log formats, you break existing tooling. So that's a point for discussion. It's another challenge to the implementation of the recommendations. Next slide, please.
Okay.
Okay, so I've only 5 minutes, so I just wanted to summarize and say that the absence of primarily source port information in logs is a big problem from a crime attribution and a public safety point of view. And this was a point that was made by Europol in 2014 and repeated again in 2016 in their crime, I forget what the document is called, some sort of crime problems on the internet. And as I mentioned earlier, logging of source port wouldn't make the crime attribution problem go away, but it does address the problem of these address sharing technologies to a certain extent, not in all scenarios, but it certainly would improve things. And I'm suggesting that the current best practice needs revision to address more of the practical issues with logging source port. It's not just say source port should be logged, but also to make some, a more encompassing set of recommendations that can actually maybe help make it happen. And then last slide, please. And in order to move the discussion along, and being completely new to engaging with the IETF, I wrote up a document and I published it, which is now in its second draft, and the link is there for anyone who wants to read it or comment, or my contact details are there and everything. So that was everything that I wanted to say. Thank you very much.
Thanks. So we're at the time limit, but if people were willing to ask questions and stay a couple of minutes longer, I'm going to let the mic open.
Okay, no.
Christian?
It's just a very brief question. It's a question of clarification. Are you asking for this log in just the network that implements the NATs, or do you have also the same requirement from servers that implement the information processing?
Yeah, no, that's a fantastic question. And the answer is it's the servers who are logging, not the NAT. The NAT itself, as I mentioned in my intervention on Tom's talk, most people who are running a NAT have a regulatory obligation to be able to identify if a law enforcement agency comes to them and goes, who was using a particular IP address at a particular time, they have to be able to tell them. The problem is, in cases of carrier-grade NAT, if the law enforcement officer doesn't also have the time and the source port, they can't even ask the ISP. The ISP will say, 1 million people were using that IP address at that time, or, some large number of people, and without the source port and the timestamp, we can't tell you. So there's an information gap between the information that's being retained in NAT scenario, in some carrier-grade NAT scenarios, versus the information that is being retained at, let's say, for example, a victim. So, for example, if you were a website and your website got hacked, and you would like the person who hacked that website to be caught, if you don't have the source port and the timestamp, you don't stand a chance. The IP address is not enough.
Thanks for the clarification.
Okay.
Thanks. Back there.
I'm Alain Durand. I'm one of the authors of RC 6302. And I take your point on the timestamp. Maybe the recommendation we made at the time was too restrictive. We'd be very happy to work with you to update the document. Now, about the other recommendation that you seems to be calling for, it was not clear to me how they could be expressed in terms of things we could put inside of a updated version of a document, but maybe we can have an offline conversation about that. We'd be happy to work with you to update the document.
Okay. If I can just very briefly respond, I think what needs to be done in that respect is to broaden perhaps the scope of the document to include not only server recommendations for somebody who's logging a server, but recommendations for people also who are implementing server software and people who are, so that could include something like, for instance, server software should be able to log source port and should be able to do it in a way that doesn't impact the performance of the server, things like that.
When we wrote the document, we were expecting that people who are operating the software will go talk to their vendors to do it, but apparently this has not happened, or the recommendation was not strong enough, so maybe we can reward this, yes.
Yeah, and further, there are also scenarios where people who are writing in-house software and who are trying to comply with best practice might be interested in implementing the recommendations themselves, not only vendors, but also, end users who are writing their own software.
Michael Abraham. So I've been successful in using carrier-grade NAT port block allocation so that one IPv4 address is shared by 16 people. And I just say, okay, you want to know who had that IP address at that point in time? It's one of these 16. It's not millions, it's 16. And I mean, police will immediately rule out most of them and will say it's one of these 3, and then they have something to go on. It doesn't have to be millions if you do the carrier grade NAT right. Just spraying the connections of millions of users randomly across huge base of IPv4 addresses just doesn't work. Does anyone actually do that? I mean, it's never millions in one IP address.
Well, no, obviously not millions. Millions, I'm being slightly facetious, but I am aware that I think it's in Belgium, they have a regulatory obligation to be only allowed to have 16 people using one IP address at a particular time. But that's not the case everywhere.
I know.
And yes, I am aware of the situation in Belgium, and that there are that has had I guess a positive side effect of they are now using IPv6 an awful lot more than carrier grade NAT. But IPv6 also then comes with its own separate can of worms, but that's another discussion.
I'm cutting the line after. Sorry,
yeah.
I'm cutting the line.
Okay, sorry, thanks.
Yeah, Suresh Krishnan. So like as responsibility here, so like I want to like not focus on the content of the draft at this point. Okay, so like the idea of presenting this here is to figure out if there's interest in updating 6302. Okay, like Alan said, like okay, maybe there's like stuff to be done, and I want the working group to own that work. So that's the first step we want to figure out. Like sit down and like ask the working group at some point, like on the mailing list, or if you want to do a hum here, that's fine, but we are probably running out of time. But ask on the mailing list, like do we want to update like 6302 to make it like more practical? So what are the changes that need to get done? So that's really what I wanted to get out of this, saying like there's some feedback saying the recommendations we made are not practical. Okay, so the question is we need to maintain our work. So that's really the reason I got like Dave to come and present here.
Okay, thanks Suresh. And finally, Eric.
Eric Vink, this time PhD Council of Belgium. It's not a regulation in Belgium at all. This is a voluntary code of conduct by ISP and other parties.
Okay, I didn't realize. I didn't know what the basis was, but I was aware it was done in Belgium. Yeah, thanks.
Okay, so thanks everyone for staying a few minutes longer. Thanks, Dave, for the presentation.
Thank you.
And we're done. Bye-bye.
Bye.
Oh man, many people in this case didn't do that.
Do we have some more blue sheets somewhere there that you can pass by, please?
I think they returned us both, but I'm sure there is more in the room than what
that they actually signed.